Hey guys, and welcome back to another video on the channel. Today we're going to be looking at something a bit interesting. So we're going to be looking at pretty much a mathematical wormhole. So what I mean by that is there's pretty much a way to create a mathematical wormhole such that if you use complex numbers. So I'll show you what I mean by that. So for example, if you had, let's say, just a standard coordinate axis, so x and y, okay? And let's say you want to go from point, let's say K, and to point L, okay? There's two ways you can get to it. There's some arc you could take, or there's a straight line, isn't there, okay? Now, which is shorter? The straight line would be shorter, mathematically. That's what we've been told. And it's always going to be shorter because if you were to go on this path here, the only way you could get to there first is if you're traveling faster. But if you're traveling at the same velocity, this distance here, it will always be bigger than this straight line here, okay? So let's label this is some arc length S, and let's label this as some line just C, okay? So what we know from this is S can pretty much be any path. Now this drawing here, this isn't just this one drawing, this S can represent any path, like this path here, or this path up here. It can represent pretty much anything, okay? But no matter what path it is, it will always be bigger than C. C will always be a shorter path. The only way that S can be a shorter path, well, it will never be a shorter path, it can only be an equal path, is if it was C itself. So in other words, S over C is always going to be greater or equal to 1. Now let's say this is just some point, I don't know, like some point x of a. As x of a approaches 0, so this is true as the limit as x of a approaches 0. So as this point goes on top of this point here, no matter which path you take, this will always be true, pretty much. Now, this is all fine with just real numbers. So this is real numbers, so it uses normal, just numbers, so only real numbers, so like irrational numbers, square root of those fractions. But if we take a look at some other way, so let's take a look at, like, if we used a complex function. Now, it's physically impossible to visualize a complex function because it comes down to this problem here. Can you visualize the square root of -1? You can't, can you? If I asked you to draw a picture of square root of -1 of how many oranges, so let's say you had square root of -1 oranges, you can't physically draw that. It's imaginary, it's not real. So we denote the square root of -1 as I. So if a complex function basically means pretty much just a standard function, but it's got I in it, okay? So if we had, let's say this arc length was modeled by a complex function instead of just a real function here. So this here, this identity is pretty much when it only encompasses real values, okay? So where x belongs to pretty much only real values, okay? But now let's take a look if this had a complex function instead. So let's just say, let's say the function modeling this arc, well, modeling this curve here was just like, let's say y equals x squared plus ix. You wouldn't be able to graph this, even though you can graph, like, let's say I got rid of this term, you could graph that, that would just be a parabola. But as soon as I put in ix, you're thinking, all right, what would y be, etc. It's a bit weird. You can't actually draw this, you can't visualize it, but we can still do the math of it. Now, the arc length of any curve, regardless if it's complex or normal, the arc length is pretty much from its starting point. So here we're saying it starts from 0 up until x of a, okay? So the arc length is the integral from 0 to x of a over the square root of 1 plus dy dx all squared, okay? So how can we find dy dx? Oh, we can just differentiate our function. Even though we don't know what this looks like, we can work out pretty much a gradient function from it. So dy dx is just going to be 2x plus I, okay? And all we got to do pretty much is just substitute this here into here, and then just play around with it a bit. So our arc length, so this s here represents this arc length, so we can find the length of this arc. But we're saying it's modeled by this particular function, so it's not really generalized anymore, so we've actually given it a specific one. Now we don't know what it actually looks like, so we can't actually draw it, but we can work out how long it is. So the integral from 0 to x of a over the square root of 1 plus 2x plus I all squared, okay? Alright, how can we work this out? So if we have 2x plus I all squared, that's the same as 2x plus I multiplied by itself. So all we got to do is first add inner last, so multiply by this. So what we get is 4x squared plus 4xi plus I squared. Now I squared, since I is the square root of negative 1, I squared is just negative 1. So what we're left with is 4x squared plus 4xi minus 1. So therefore we replace that in our integral here. Our arc length is the integral from still 0 to x of a over the square root of 1 plus 4x squared plus 4xi minus 1. Boom, boom. Okay, now we're left with is pretty much just this. So s is this integral still from 0 to x of a over the square root of 4x squared plus 4xi. Okay, now we want to see what happens is as this value goes, like this point goes on top of this point k. So in other words, we want x of a to approach 0. Now, if we take a look at these functions in here, we can approximate this integral. We can make it simpler. Of these functions here, which one of these, as x gets really small, so as x, x of a goes to 0, which one of these functions is going to hit 0 first? Will it be x squared or just x? So if I put in 0.0001 into here, this one's going to give me a smaller number than this one here. So in other words, this function is going to approach 0 faster than this one. So what we can say is we can actually approximate this integral. As x of a goes to 0, we can approximate it and say, alright, the arc length is approximately still our integral from 0 to x of a. But we can substitute the 0 into here, and we're left with just the square root of 4xi dx, okay? Now, we can do this integral quite easily now. So s is approximately the integral, so integral from 0 to x of a, splitting this up as a third, so we can treat this as the square root of 4i square root of x dx. Now we can integrate the square root of x pretty easily, because we know that's the same as to the power of a half. So all we got to do is add 1 to the power. So we have x is 3 over 2 divided by that, so it's 2 over 3. And then all we have is the arc length is approximately 2 over 3 x 3 over 2. And then, oh, we've also got this square root of 4i. I'll just go move that real quick. So the arc length is approximately this 4i, and then our bounds here. Now, all we're going to do is replace x with x of a, because if you put 0 into here, it's going to turn to 0. So our arc length, our approximate arc length for this complex function is the square root of 4i to x of a 3 over 2 over 3. Okay, so this is our approximate arc length or our complex function. Now we don't know what our complex function looks like, but this is approximately the distance it travels. Okay, alright, so now we've got to compare two things. Alright, so we're comparing the arc length. We want to now compare a straight line. So our straight line of pretty much between these 2 points is still going to be, for example, it's going to be pretty much just like Pythagoras' theorem. So to find the line here, it's going to be the square root of pretty much just, for example, x of a, some x of a, and whatever y value that gives you, so plus y of a, okay? So if we had our function here, so y equals, what was it, x squared plus ix. So if you want the y value when x, so you can work out y of a. Y of a is when x is equal to x of a. So all we're going to put is x of a in here, and that'll give you y of a. So y of a is going to be x of a all squared plus x of a, sorry. Okay. So the reason this is good is we can actually substitute this stuff here into here. So in other words, c is going to be the square root of x a all squared plus all this all squared, so x of a all squared plus I x of a all squared. Okay. Now we can work this out quite easily. We just gotta expand this. So x of a squared plus I of x of a multiplied by itself is going to give us, so multiply this term here, that's going to give you x of a to the 4 plus multiply this term here, but we have to do that twice. So what we're going to have is 2i x of a to the 3, because you're multiplying here and then you're also multiplying here, sorry. And then our last term is going to be plus I squared, and then let's move across a bit, I squared a x of a. Okay, so what we're left with is our function is this here, 2i a minus a squared. Now you notice that's all squared, sorry, nearly got that wrong. So our c here, so if we put that into here, we're going to have this, so x of a all squared plus all this, so x of a to the 4 plus 2i x of a to the 3 minus x of a to the 2. So we can see that cancels with that, and now we've got an we've now basically got an equation for our line here. So our line from 2 points of this complex function here is pretty much going to be a of x to the 4 plus 2i x of a to the 3. Okay, now we can simplify this because we can take out a factor of, what can we take out? So we can take out a factor of a squared out of here, so we're left with a xa squared plus 2i xa, and this is all under a square root, so this is going to be just x of a square root x squared of a plus 2i x of a. Okay, so this is our c. Now in the real world we had this pretty much inequality here. As x of a goes to 0, the arc length will always be bigger than c. This is what this pretty much means. Let's see if it's true in the complex plane. So in other words, what was our expression for our arc? So our arc was here, so let's take that now and let's bring it down here. Now it's hard to, we actually can't physically draw this diagram because of our function, but we've got to see what actually happens. So we've got to basically see, alright, as the limit as x of a goes to 0 of s over c. Let's see what happens. So let's substitute this here at the top. So we get the square root of 4i 2 over 3 x of a 3 over 2. Okay, divided by x of a square root of x of a all squared plus 2i x of a. Okay, now you're probably thinking, how are we going to start cancelling this? Well, for starters, I think we've done it all correct. Oh, there's one bit we haven't done, sorry, before we do this real quick. We've got when we're doing our straight line here, so we simplified this arc here. Where was it? We simplified, oh, we moved it. We simplified this arc here when we let pretty much as soon as x of a approached 0, this function went to 0 faster than this one. We've got to do that the same with this line here. We forgot to do that bit. So if we let, so as a of x of a approaches 0, which function out of these ones is going to approach 0 the fastest? It's going to be this x squared here. So we can actually just cancel that out. So c is going to be x of a over the square root of 2i x of a. Okay, that's it. All right. So we want to see, alright, the limit as x of a goes to 0 of s over c. We've got to see what happens here. So top function, we're going to have a square root of 4i. Then we're going to have 2 over 3 x of a over 3 over 2. So this is our s divided by x of a over the square root of 2i x of a. Now, we've got to see what happens here. Now, there's a couple things we can do straight away. So we know if we were to distribute this into here, this is equivalent to this thing up here. Because if we take a look at this, so x to the power of 3 over 2, that's equivalent to pretty much just x times by x to the power of a half, which is actually what we have down here. So we can cancel pretty much that, and that straight away. So all we're left with is square root of 4i, 2 over 3, over square root of 2i. We have a square root of I up here and a square root of I down here, so that can cancel straight away. So what we're left with is pretty much square root of 4, which is 2, times by 2 over 3, over the square root of 2. So what we're left with is pretty much, alright, 4 over 3, multiplied by, since it's divided by the square root of 2, multiplying by 1 over root 2. 1 over root 2 is the same as the square root of 2 over 2, if we rationalize it. So we have this here, multiplied by root 2 over 2. So we effectively have, so cross cancel, we have basically 2 root 2 over 3. So this is the ratio of S over C. Now, if you put this into a calculator, this approximately equals, where's my calculator? Alright, this one is not turning on. This one will. Right. If you put that into a calculator, it's approximately 0.9428. Now what does this mean? This is a really special number. So what this means here is, alright, so the limit as x of a approaches 0 of S over C is equivalent to, what was it? Oh, no, approximately, is equivalent to, what was it, 0.94228. This means that our arc of our pretty much our complex function is shorter than a straight line. Now that's hard to imagine, because if you take a look at a real function up here, you can always see, alright, this is always going to be the shorter distance compared to this. But with a complex function, it's shorter. So imagine like this imaginary arc. You actually can't draw it. This curvy boy or line, this curvy like path is shorter than a straight line, which is insane. So what this basically means is, alright, this is, alright, minus that from 1. This means that pretty much S is 6% shorter than C. So this means if you're traveling along a straight line, when you're 94% of the way there, on this curve, this complex curve, you've already made it to your point here. So basically, in order for that to be true, it's pretty much covered pretty much it's covered a small distance in no amount of time, and hence the curved path, our curved arc, it's pretty much wormholed. So this is pretty much a mathematical wormhole, because in order for this to be true, like, it's just insane to think about, because this curved arc can never, like, it's shorter than this straight line path, and the only way for that's true, it's pretty much wormholed to this, like, these 2 points. So imagine 2 points in space, and this curved path has reached there before the straight line, so and hence it's actually covered pretty much. So when the line here, so the straight line is here, the curved boy has already gotten to this point here. So it's pretty much like wormholed, which is insane to think about. So this is like a mathematical wormhole. Now, it's really hard to imagine this because you can't actually draw a picture of this complex function here, just because of this little number here. Anyway, I hope you found this video kind of cool. It's insane to think about, and yeah, if you enjoyed it, like and subscribe.